This video is going to look at the shapes of molecules for A-level chemistry. Here we will focus on the simplest structures. What you'll be expected to do for A-level chemistry is to draw the 3D shapes of different molecules, identify their bond angles, and name the structures that you have drawn. So the easiest thing to do is to go through some examples. So down the left-hand side here, we're going to run through these different examples of shapes. First of all, we'll look at beryllium fluoride, so BeF2. So for this, what you need to do is identify the central atom. Now I've drawn the central atom in red here for all of these examples. So for our first example, we've got beryllium being our central atom. You need to identify the group in the periodic table that your atom belongs to. So beryllium is in group 2 of the periodic table, so that means there are 2 electrons in the outer shell and therefore 2 electrons available for bonding. The next thing you need to do is look back at your structure and you'll see that there are 2 fluorines bonded to that beryllium, so that's 2 more electrons available to bond. After that, what you need to do is add those 2 numbers together to get the total number of electrons available for bonding, divide that by 2 to turn it into pairs of electrons. So this means there are 2 bonding pairs of electrons in BeF2. In other words, there are 2 bonds in BF2 because there are 2 pairs of electrons for the 2 atoms bonded, and there are no lone pairs of electrons left over, which we will focus on in the next video. So to draw this structure, beryllium at the centre with the fluorines either side, we have a linear molecule and the bond angles are 180 degrees. So that's all you would have to do for this particular molecule. So that's the basic example for this one here, for BeF2. We have 180 degree bond angles on a linear molecule. Let's focus in and look at BCl3. So again, the central atom, identify the group of the periodic table it is in, so that you know how many electrons are available to bond. So boron is in group 3, so there are 3 electrons available to bond for this molecule. Then identify the number of atoms that are bonded to the central atom. Now, each one of these examples, these atoms are all the same, but you would just count up the number of each type of atoms bonded if they were different. So there are 3 chlorines bonded here. That gives us a total number of 6 electrons available. Divide that by 2 again to find out pairs. So that's 3 pairs of electrons. If we compare back and have a look at BCl3, we see we've got 3 pairs of electrons with 3 atoms bonded to the boron. So all those electrons are involved in bonding, so there are no lone pairs of electrons in our final structure here. So let's have a look and see what it would look like. So the boron at the centre, the 3 chlorines form bond angles of 120 degrees. So here is our structure, 120 degree bond angles, and we have a trigonal planar. So this is trigonal planar molecule. Now why trigonal planar? Well, if we have a look at this molymod here, we can see that it's on one flat plane, so it's a planar molecule because it's across the flat plane, and it's trigonal because there are 3 points to it, or 3 sides, sorry. 1, 2, 3 edges to this planar molecule. 1, 2, and then the 3rd one there. So this is our trigonal planar molecule. Okay, I didn't show you on the first example, but if I just go back and have a look after this, I do have a molymod to show you the first. So for this one here, where we have our linear molecule with 180 degree bond angles, so we can see this is linear because it's on the on the flat plane here, and then we've got the 120 degree bond angles. So that's 120 degrees there. Sorry, start again, 180 degrees here. So BEF2, we have 180 degree bond angles. BCl3, we have 120 degree bond angles. Now we get slightly more complicated with CH4, with our methane. We do exactly the same thing again. We identify our central atom, carbon in group 4. There are 4 atoms, and they are hydrogen, attached to that carbon. So that's 8 electrons in total available to bond. Again, divide by 2. That's 4 pairs of electrons. If we look back at our original structure, all of those pairs of electrons are involved in bonding, so we have no lone pairs. So we will stay with a fairly simple molecule. We have our carbon in the centre here. We have a hydrogen up here, flat on the board. We have another hydrogen. This time we're going to need to draw a triangle to show that this hydrogen is coming out of the board towards you. There is another hydrogen here going away from you. So the dotted line means it's going away. And then another flat line here to show that that hydrogen is on the flat plane of the board as well. So this comes towards you, this goes away from you, and they are flat on the board. The bond angles this time are 109.5 degrees. This structure is tetra for 4, so it's tetrahedral. I have a molymod to show, so you can see exactly what this would look like in a 3D structure. So here's the molymod. You can see that if we match it up with this one, we have this one coming out towards you, this on the flat plane of the board, that also on the flat plane of the board, and then this hydrogen here is going away from you down there. So that's a tetrahedral molecule, our example being methane. The next one to look at is PCl5, where we have a slightly different structure and again slightly more complicated. We can keep using exactly the same model for working out our bond angles. So we have phosphorus here, and if you look, phosphorus is in group 5 of the periodic table, so there are 5 electrons available for bonding. We have 5 chlorines attached. That's 5 more electrons brought in. That's 10 electrons in total. So that's 5 pairs of electrons. Now if we look again, we've got 5 pairs of electrons. They are all involved in bonding because we have 5 chlorines attached. We have no lone pairs. We don't have any electrons that don't match the number of bonds in our molecule. So let's have a look at what the structure would look like. So, phosphorus at the centre. Here we have a chlorine flat on the board. We're going to have a chlorine coming out of the board in this direction, and a chlorine moving away and into the board there. So at the moment, our structure looks as if it's trigonal planar. So it has a central part, which is trigonal planar, flat on the board, coming towards you and going away from you. But obviously that doesn't complete the number of chlorines involved. The rest of the chlorines, we have a chlorine down here and a chlorine up here. I should just say that the bond angles here are 120 degrees. So these are all 120 degrees around here, just like I showed you here in this central planar part. Above and below the phosphorus are 2 more chlorines. So we have another bond angle in this molecule. We have a 90 degree bond angle here. We have 90 degrees there, to this one, down here and down there. So we have 90 degree bond angles, and our structure will look like this. So we've got the phosphorus that goes down, we've got the trigonal planar part in the middle here, and then we've got this chlorine that comes straight up. So we've got the chlorines going up and down in the middle, and then we've got the trigonal planar with the 120-degree bond angles here, and then if we have a look, you've got the 90-degree bond angles here. So this structure is called a trigonal for the 3 points in the centre. We have our trigonal bipyramid. Sorry, trigonal bipyramidal. So a trigonal bipyramidal. So if you have a look back at this structure again, there's a pyramid on the top here. If we look down, so we've got the pyramid on the top there, and then we've got the same thing underneath. We've got the pyramid here. So it's a double pyramid. So bipyramidal. The last structure to look at is if we've got 6 bonding electrons attached to our central atom. So SF6, again, in exactly the same way, we can work out the number of each type of bonds and the bond angles simply by looking at the group our central atom is in. So we've got sulfur in group 6. We've got fluorine, and there are 6 of them. That gives us a total of 12 electrons available to bond, which is 6 pairs. Have a look back at our original structure, our SF6, sulfur hexafluoride. We can see there are 6 pairs, there are 6 fluorines, so there are no lone pairs. All of the pairs of electrons are involved in bonding. So let's draw the structure. Sulfur in the centre. We have 2 fluorines coming out of the board. We have 2 fluorines going into the board. So that gives us 90-degree bond angles here in the centre. So these are all 90-degree bond angles, 90 there, 90 there, 90 there, and 90 there. So in the centre, it looks as if we have a square planar molecule. But there are the other 2 fluorines to put in as well. So there's the fluorine above and the fluorine below. Again, we have 90-degree bond angles between all of these. So it's a slightly easier structure to look at. This time, we have an octahedral structure. And if we have a look at the molymod, this is the molymod. So we've got 90-degree bond angles in all directions for our octahedral molecule. What we can see is that whilst it has 6 points, it actually has 8 faces. So we've got 1 face here, so that's 1, 2, 3, 4, and then it's repeated again on the other side, so there are 8 faces, which is why it's called octahedral. So just to recap, our first example is linear with 180-degree bond angles. This is trigonal planar. With 120-degree bond angles. Tetrahedral with 109.5-degree bond angles. We have trigonal bipyramidal and here we have both 120 degrees in the centre and we have 90-degree bond angles to the chlorines that go up and down. And then our final structure is octahedral, and for this all the bond angles are 90 degrees. So that's just a run through of the simple shapes of molecules. In the next video we're going to look at what happens when you get lone pairs of electrons.